Okay, I'm going to review the test for the most part now. So it's funny here, like you don't go in the room. I'm like talking like a classroom, right? So, so I know that there's others of us here. It just happens to be one person in the room right now, so it's a little awkward. But at any rate, I'm going to be mostly covering the exam for now. So if you have specific questions, just type into the chat box or alert me if you want to. If you have a microphone, you want to talk, want to be able to be heard here, and I'll make sure that I turn on your mic temporarily. Otherwise, I leave the mics muted. I mute you guys as you log on, so we don't get a lot of background noise and echo and stuff like that. So the first thing that I want to cover is before we actually make sure this is still working. Yeah, it sure is. Before we actually get started, I want to just quickly cover how to interpret the table for the z-scores. Okay, so we have a normal distribution. Okay, normal distribution is bell-shaped and it's symmetrical, kind of something like that. The mean and median are in the center, right? I'm going to make up a mean here call this a mean of 500. And the standard deviation represents the spread of that distribution. So I'm going to call this a standard deviation of 50. I'm going to call it a standard deviation of 50. So what that tells us is that half of the distribution is above 500 and half of the distribution is below 500. This could be dollars. It could be some level of enzyme in the bloodstream. It could be many things, right? But I'm just going to call it 500 for now. Just use it as a number for right now. Okay, so that tells me that the way this distribution is spread out using the empirical rule, which is just an estimate of how the distribution is arranged, using the empirical rule, that if I go one standard deviation below the mean, which would be a value of 450, and one standard deviation above the mean, which would be a value of 550, that's 68% of the area of this distribution, which also represents the percentage of this population, which also represents the probability that if I randomly pick one person, that I would pick somebody between those two numbers, 450 and 500. Okay, if I went out further to two standard deviations below the mean and two standard deviations above the mean, that would be 2 times 50. So this would be a value of 400, and this would be a value of 600. That would represent 95% of the population, or the probability is 95% that I'd pick somebody between 400 and 500 if I pick someone randomly. Well, there's a lot of things that we can do here. For instance, I could see that between 450 and 550, that's 68% of the population, and the mean divides that in half. So I could argue that this is about 34%, and this is about 34%. So now I know between 450 and 500, 34% of the population, right? I know, for instance, that between that under 400, well, how much would that be? What percentage? Well, between 400 and 600 would be 95%. That leaves 5%, but it's got to be divided between the tail and the top and the tail and the bottom. So that makes that 2.5%, right? So now let's talk about if we have a problem now that involves this distribution. I'm going to take the same distribution, I'm going to sketch it again. Okay, here's the mean. It's 500. And the standard deviation again is 50. Okay, so now let's say I asked you what percentage of this population, what's the probability of being less than 500? Right? What's the probability of randomly selecting someone that's less than 500? Well, 500 is the mean. So half of the population is below the mean. So that area is 50%, 0.5, right? Okay, so now what if I asked you, what's the probability that I would select someone randomly that is under 450? Well, 450 would be one standard deviation to the left of this. So 450 would be about there, right? 400 would be about there, 550 would be about there, and so on and so forth. So if I want to know what's the probability of selecting someone that's less than 450, right? What's that probability? What's going to be the area to the left of 450, below 450? Well, let's take a look. Well, it's going to be roughly 16%. But we're now actually going to go a little further here, and we know that the z-score for 450 is one standard deviation below the mean. In other words, it's -1. Now, just so that you can see how I get that, z is equal to the value you're interested in minus the mean over the standard deviation. So that's going to be 450 minus 500 over 50, which is minus 50 over 50, which is -1. -1 indicates that it's to the left of the mean, right? If we're to the right of the mean, that would be 550 minus 500 would be a positive number. So it's -1 is that z-score, that number that represents 400 in number of standard deviations. Z-score also means you could translate that in number of standard deviations to the left or to the right of the mean. So let's look up what area is represented by a z-score of -1. So let's see, -1 is going to be on this. We have 2 pages for our z-score. And notice that it shows us that the areas that are represented in here, the z-scores and the areas that are represented, are always measured from that point that you're looking for, that z-score you're looking for, to the left below. Okay, whether it's a negative z-score like this one, so it's on the left side of the mean, or a positive z-score like this one, where it's still measuring to the left, numbers below that, the percentage below that. Okay, so let's look up -1. -1.00 is 0.1587, not quite 16%, but that the empirical formula is really kind of an estimate, right? So this area here is 0.1587. Okay, so now if I had asked you, what's the probability of selecting someone from this population that's greater than 450? What's that probability going to be equal to? Oh, hang on a second here. Greater than 450. So we're looking for the area to the right. So it would be 1 minus 0.1587. Or if this is 16%, that would be about 84%. Right? So that's the deal. We're looking for since I'm looking for greater than 450, I'm looking for the area to the right. Now, if I really want to be tricky, I might ask you, okay, well, what's the probability of selecting someone that's less than I'm going to make up a weird number, 520. Okay, so let's see, what's that z-score going to be? That z-score is going to be equal to 520 minus 500 over 50. So that's going to be equal to 20 plus 20 over 50 is going to be equal to 0.4, right? So that's a z-score of plus 0.4. So if I go to the table, I'm going to go to the positive numbers. So a z-score of plus 0.04 is 0.6554. Okay, so I'm going to go back here to my sketch. So 520 is going to be around here somewhere. That's going to represent a value of 520, which is a z-score of 0.4 plus 0.4. So if I ask you what's the probability of being less than 520, from the table, it's the area to the left here. So the probability of being less than 520 was, what did I say it was? I forgot already. 0.6554. 0.6554. Okay, so that's the area from here to the left, right? What's the probability of being greater than 520? Right? Exactly, it's going to be this area here, so it's going to be 1 minus. Okay, see how simple this is, really? Okay, now what? Now I'm going to make it really complicated. What's the probability of being greater than 450? Let's see, greater than 450 and less than 520 between these two. Well, no, hang on a second. That would have been if it would have been a +1 z-score, right? So it's this area in between these two. So let me think about this. Everything from here down is 65%, right? Everything from here down is 15.87%. So the difference is going to be if I take away that 15.87, it's only going to leave the area I'm interested in between 450 and 520. So it's 0.6554 minus, right. That's why it's so important that you draw this. because it makes it so much easier to understand when you actually sketch it out. Okay, good. All right, so the rest of you guys are catching up. You'll be able to watch this later on when I put it online. You'll be able to catch up to where we are now. I'm going over the exam. If you guys have any particular questions on the exam, because we're going to start on a new topic when we come back on Monday or Tuesday when you get your material, depending on which class you're in. We're going to be starting a new topic, which is we're going to try to start working with how sample distributions behave. Right now, I'm dealing with a population. Remember, notice I'm using mu and sigma. I'm dealing with the entire population, normally distributed population. Next week, we're going to be talking about what happens when you take a sample from that population, because in real life, we're always working with samples. We're never working with the entire population. Okay, but we're trying to understand that. So if you have a specific question about the midterm or any of the work up to that, just tune in and let me know. Okay. Okay. So I'm going to start at the top. First of all, this table. You guys have trouble with that table? I think we went over this a couple of times, and hopefully it didn't cause too much trouble. How many of the patients stayed at the center for less than 7 days? And the frequency, the height of the bar represents the frequency, the number of patients that were there for 4 days, 5 days, 6 days, 7 days. So for less than 7 days would have been two people stayed for 4, 3 stayed for 5, 1 stayed for 6. So this is going to be the sum of those, which is what, 6? Yes, 6. 6 patients did. Okay, what's the probability of staying in the center? This is a little bit more complicated. What's the probability of staying in the center for fewer than 7 days? Same question. Given that the patient has stayed for 11 days or more, what's the probability that that patient stayed for 14 days? That's a conditional probability, right? So we set the original condition we said is that given only the patients that stayed for more than 11 days, for 11 days or more. So in other words, how many patients is that? That's going to be 2 patients, 5, 7 patients, 9 patients, 10 patients stayed for 11 days or more. How many of them stayed for 14 days? Just 1. So the probability is 1 out of 10, or 10%, right? See, it's that simple. Like I said, once you start to understand this stuff, it becomes simpler and simpler. I'm sorry? Unless you have other questions. Do you have other questions? No? Okay, yeah, I'm not new material next week. Okay, good night. Okay. So at any rate, like I said, if you guys show up for this session, this is like a voluntary session. So if you ever show up here or tune in online or something like that, you don't have to, let me know or anything. You just pop in or leave whenever you want to. That goes for you guys online too. If I'm boring you, don't worry about it. I won't feel bad if you drop out. And if everybody drops out, trust me, I've done this before. I just keep talking as if I'm, there's people in the room. What's the probability of saying? Okay, let's see. Next. We got that, I think. Okay, now diagnostic tests. Okay, a few people had some issues with that. Hopefully not too many. Okay, what's the prevalence? I actually put this on a spreadsheet also so we can work with it if necessary. Well, we're assuming that this is a random selection from this population. We randomly selected 100 people. What's the prevalence of this disease in this population if it's a random sample? How many people did we sample? 1,000 altogether, right? How many of them have the disease? 100, right? Some of them tested positive, some of them were incorrectly tested negative, but the total number of people in this disease column, people that had the disease, is 100, so the prevalence is 10%. Okay? What's the sensitivity of this diagnostic test? Sensitivity is the percentage that it gets right on people who have the disease. In other words, what percentage of people that have the disease got identified with a positive test? So out of 100 people who have the disease, how many of them correctly got tested positive? How many true positives? 90. So that's 90 out of 100. The sensitivity of this test is 90%. Okay, now the next thing I'm not even going to scroll down. I'm guessing the next question is going to be, what's the specificity of this test? And the specificity is how good is it at identifying people that don't have the disease? How many people don't have the disease? 900. Out of those 900, how many did it correctly identify with a negative test? 702. So the specificity is 702 over 900, which turns out to be about 78% specificity. Is that right? Yeah, specificity is 78% for this particular test. Okay, so now the next thing, we'll drop the next shoe. What's the positive predictive value of this test? Now, all we're interested in is positives. When we say positive predictive value, you take this test, the doctor tells you you've tested positive. What's the probability that you actually have the disease? Well, how many people tested positive? 288 people tested positive. 90 of them had the disease. 198 of them tested positive, but they don't have the disease, right? That was an incorrect test. That's what they call a false positive, right? This is a true negative, true positive up here, right? They have the disease, they tested positive. This is a true negative. They don't have the disease, they test negative. This is a false negative. They tested negative, but they have the disease. And this is a false positive. So 288 people tested positive, but only 90 of them have the disease. So what's the probability of you having the disease, the positive predictive value of the test? It's 90 over 288. Okay, and that's going to be 31%. Right? It's only one chance in three that you actually have the disease. A lot of tests are like this, especially when they apply it to a large population that has a relatively low prevalence of that disease. Okay, and in fact, next question, what's the negative predictive value of this test? Okay, how many people tested negative? 700 people tested negative. How many of them actually don't have the disease? 702. So the negative predictive value is 702, number of people that tested negative that don't have the disease, over 712. So that's 98.5%. And which of the following is a true statement? This was a tricky one. Okay, I checked. It's already, you can see it's already checked off which one's right. The positive predictive value will decrease when a diagnostic test is applied to a population with a lower prevalence. We've brought this up a number of times. Why does that happen? Because if it has a low number of people that have, in other words, if I go back up to this table here, 900 people didn't have the disease, 100 people did. Now, if that were 9,000 people that didn't have the disease and 100 people that did have the disease, well, we have so many more people that are going to test false positive than if it were a population where the prevalence was very high. So we have a lot more people that don't have the disease that we can incorrectly identify as positive. So the positive predictive value goes down when the prevalence is low. I think we tried it a couple of times, a couple of ways in class. Same specificity, same sensitivity, but we only changed the prevalence, and we saw that the positive predictive value went down. Okay, so what's the probability? Okay, now, this is another one that caused some people some problems. Okay, let's talk about this. Now, this is what they call a binomial distribution, right? Binomial distribution is like a normal distribution, but it only deals with situations where you have two choices, true or false, male or female, and so on and so forth. So what might that be? Diabetic or not diabetic? Right. Okay. Or BMI under 30, BMI over 30. Right. Two choices. Right. So in this particular case, we're talking about whether or not a person that's over 65 will fall or they won't fall. So the probability of falling is 1 in 3, 33%. Right. If this room was full, had 100 older people in it, 33 out of those 100 people would have a fall during that year, right? That's what this is basically predicting, right? So 1 in 3 is the probability that any individual person would fall. Okay, now let's say that I picked out one person randomly in this population. What's the probability that one person over 65 will fall this year? 1 in 3, 33%. What if I asked you, what's the probability? I'm going to pick 2 people out. What's the probability both of them would fall? Be 33% times 33%, 0.33 times 0.33. What if I pick 10 people out? What's the probability all of them would fall? 0.33 times 0.33 times 0.33, right? Just like flipping a coin, 1/2 times 1/2. In other words, get 10 in a row, right? Cleveland won, how many games did they win? 21 games in a row? What's the odds of that happening? Assuming that Cleveland's an average team, what's the average, the odds of that happening? It's 50-50 each game if they were an average team, right? So that would be 1 out of 2 times 1 out of 2 times 1 out of 2, 0.5 times 0.5 times 0.5 times 0.5. If you figure that out, it's a big number. Very unlikely. That's why it happened. That's why it's a record. 125 years of playing baseball. That was I think that's the longest streak, winning streak, right? In games in a row. So that's a very unlikely occurrence because it's 0.5 times 0.5 times 0.5. So now the part that gets complicated is if I tell you that I have its probability of being diabetic in this population is 10%. But now I'm going to go out and pick 5 people from this population. What's the probability that all 5 are diabetic? Easy. 0.1 times 0.1 times 0.1. What's the probability that none of the 5 I pick are diabetic? Well, if the probability of one person being diabetic is 10%, probability of being not diabetic is 90%, 0.9. So what's the probability of all 5 not being? 0.9 times 0.9 times 0.9. The complicated part now comes in. What's the probability of getting 2 people out of 5 that are not diabetic? Well, there's just, when I say what's the probability of them all being diabetic or none of them being diabetic, that can only happen one way, right? They all have to be diabetic or they all not diabetic. But if I ask you 2 out of 5, well, the first person might be not diabetic, the second person might be diabetic, third person might be diabetic, fourth person, no, that would satisfy that. Or it could be yes, no, no, or it could be no, no, yes, or it could. There's a lot of ways that could happen. That's why we had that funny formula with the exponentials and stuff like that. That becomes a very difficult thing to predict mathematically. There's a formula for it. You could do it, but it can get pretty complicated pretty quickly. So instead, we have a tool in Excel that helps us, binom dist, that helps us calculate that. So right now, let's look at this problem. In any one given year, 1 in 3 Americans over 65 will experience a fall. Probability of a fall is 0.33 for any one individual. If you have 4 living grandparents, so we have a sample of 4 people, right? So our sample size is 4. Okay. Assuming the probability is independent, what's the probability that none of them will experience a fall? You want to know something? There's a couple of ways for us to do that. One of the ways to do that would have been to say if it's 0.33, then not having a fall is 0.66. So 4 of them not having a fall is 0.66. Yes.
I'm going to ask a stupid question.
Yes.
Where'd you get the 0.33 for this question?
Oh, 1 out of 3. 1 out of 3 Americans age 65 will experience a fall.
That's where.
Right.
Okay.
Right. The probability of any one person.
I did not read that.
Just like I could have said the probability of being diabetic is 1 in 10. Right. So that's where that probability came from. So an easier way for us to do this is to go to Excel, okay, and use binom dist. I actually had this table set up for this before. Okay, so I'm going to say equals binom dist. There's a few versions of this. They all work the same. As soon as you type in the equal sign and binom dist and put it in parentheses, Excel prompts you with what it needs, the arguments, the information it needs. So the first thing it wants to know is the number of successes. In this case, the success is a person who fell, an old geezer that fell, like me. So old fart fell down, and wound up in your emergency room, right? So how many, in the first part of this problem, how many people fell down? Okay, what is the probability? None of the grandparents, so that's 0. We're looking for 0. So the number of successes is 0, comma, and the next thing we want to know is the number of trials. What's the sample size? Sample size is 4 grandparents, right? Comma, and the next thing we want to know is probability of success. The probability for any individual falling down in this group is 33 point. Yeah, actually 0.3333, but I'm going to just go 0.33. Comma, and then it wants to know true or false. If I put in true, it's going to give me the probability for, this is really cumulative is the question it's answered. If I put in true, it's going to give me the probability for that outcome and everything below it. So since it's 0, it doesn't matter if I put in true or false, right? Because it's 0, 0, there's nothing below 0. So it really doesn't matter. Watch this. If I put in true, This is the probability. Probability is about 20% that none of the four will fall, right? Watch if I change that to false, it comes up to the same thing, right? Makes sense? So what's the next question we ask about this? Next question we ask is, what's the probability that one or more will experience a fall? Okay, one or more. Well, you want to know something? Just like our Z table, it only works from a certain number down. In other words, 0 down, 1 down. It only gives you the probability that when you say true, from that number down. So if you want to know what the probability is from that number up, you have to subtract it from 1. So the probability of no grandparents falling is 20%. So what's the probability of one or more? 1, 2, 3, 4. It's going to be 80%, right? You agree with me? Right. Think about that. Now, the probability, it says one or more grandparents. What's probably one or more will experience a fall? Well, we know 0 is the only thing less than 1, right? So 0, the probability of none of the grandparents falling is 0. The probability of 1, 2, 3, or 4 falling is whatever's left, right? So I'm gonna rephrase this question. Well, actually, let me see if I went any further with that. I didn't go any further. I'm gonna redo this question now again, and I'll make something up to go along with it. Okay. So now, what's the probability of exactly 2 out of 4 parents falling? Okay, how would I figure that out? Exactly 2 is equal to binom dist, parentheses, and the number of successes is 2, the trials is 4, the probability is 0.33, and for cumulative, I'm going to put false. So if I put in false, it gives me the probability only for that exact outcome, exactly 2. Not 1 out of 4, not 0 out of 4, not 3 out of 4, not all 4. Only for that exact outcome, 0.29. The chances of getting exactly 2 out of the 4 experiencing a fall is about 29%. Okay, what's the probability of getting 2 or fewer experiencing a fall? Okay, it's going to be the same formula. Use binom dist, right? Parentheses, number of successes, 2 or fewer, 2, 4, 0.33. 2 or fewer is going to be true now. So that's going to give me the probability for 2, 1, or 0, everything to the left of that, which is 89%. What's the probability of getting more than 2 that experience a fall? Well, 2 or fewer is 89%. So more than 2 would be what's left. 3 or 4, which is going to be 11%, right? 1 minus the 89%. Okay, what would I put in there if I ask you, what's the probability of getting 2 or more? This is going to be as complicated as it gets. How would I figure out the probability of 2 or more grandparents falling? Keep going. You have to put 1, right? Because 2 or more, you can't go that direction. You can only go the other direction. So 2 or more would mean that it would be 1 or 0 is what you want to exclude. So you figure out the probability for 1 or 0, right? Say true for cumulative 1, 4, 0.33, and true for cumulative, it gives you the probability for 1 or less. That leaves 2 or more. Okay? When you go over this later on, if you listen to the video, if you go through the video again and stuff like that, think about it carefully. When things are quiet and stuff like that, and I'm sure you're going to be able to figure this stuff out. Okay, and all these problems are just some way of manipulating these questions, just like before. What's the probability being between these two numbers in the normal distribution? Well, we had to visualize what area do I get when I use the Z table to give me this? What area do I get when I do this? And then what areas I'm really looking for. So that's how you deduce what you subtract from what. You've got this area over here, but you really just want this part of it, so you need to find a way to extract that from it, get that part out. Okay. Let's see. Oh, okay, and then we had a problem that involved an Excel or SPSS. You could use Excel or SPSS for this one. That asks you to calculate the mean, the standard deviation, okay, and it's also then to separate it out by gender, right? So you could use let's see, where do I have it? High school, heights, follow close to the main territory. Here it is. Standard. Well, if we use Excel, I don't have the file handy. If you use Excel, the way you would do this, I'm going to just make a list of numbers here. Whoops, we do it here. Right? If we're looking for the mean, you're just going to use average. Parentheses, and you'd indicate that length, that group of numbers. It would give you the average. For standard deviation, you would just stick that standard deviation in here. Okay, and I'm going to go. I'll actually maybe download the. See how much time we have. I'll download these, and we'll actually use the files themselves. And that's the standard deviation for those whatever group of numbers that we have there. The next question, though, says the heights of 10-year-olds, regardless of gender, closely follow a normal distribution with a mean of 55 inches and a standard deviation of 6 inches. Use this distribution for the following questions about height. Now we're back to the Z table, right? Okay. What's the probability that a randomly chosen 10-year-old is shorter than 48 inches? Well, the mean is 45 inches, so that's going to have a negative Z-score. It's going to be to the left of the mean, 48, right? So I'm going to sketch it. Okay, let me get this out of the way. Let me see if I can. Okay, where did that go? Here it is. Okay, yes, Josette got that right. Good. Okay, let's see. Okay, drawing our normal distribution again. And the mean was 55, and the standard deviation was 6. And we were interested in the probability that a randomly chosen student was less than 48 inches, right? So if we're interested in the percentage of this population that's less than 48 inches, we're looking at the area in here. Well, that's a natural, because we know we can use it, find the Z-score for 48, and we're just interested in the area to the left of that. So that's exactly what the Z-score tells us. But now let's see what the Z-score is. Z-score is going to be equal to 48 minus 55 over 6 is equal to 7 over 6. What does that come out to? 1.166. Okay, 1.166, good. Okay, so now let's go to our Z table, and that's a negative 1.66, right? That's a negative 7. That's a negative 1, so we know it's on the left side of the distribution. So if we go to the negative Z-scores to the left of the distribution, it's negative 1.1, 1.16, 1.16. Now the 6 we have to go across to the 6th row. 0, 1, 2, 3, 4, 5, 6. So it's going to be 0.123. It's convenient. I won't forget that, right? So this area in here is 0.123 or 12.3%. 12.3% of this population is below 48 inches tall. What percentage is above 48 inches tall? 1 minus that. Exactly right. That's the percentage of population that's above that. Okay, so now the next part of this question was, let's see, what's probability randomly chosen. Okay, that's good. That's good. The probability at where do we go? I'm not reading the question, am I? It's shorter than 48 inches. There's another part of this question that I'm not seeing here for some reason. Yeah, I did that. Then when we went on to, oh, here it is. It's the probability is between 60 and 55 inches. Oh, that's a curve, right? Okay, so let's take a look at that. So I'm going to redraw this. Uh-oh. My tablet died. Oh, man. I need a new table. Every time I get it working, it goes out again. There we go. Okay, I'm trying not to move it. Let's see. Oops. Same distribution. That's an ugly one. Okay, 55 inches was the average. Standard deviation was 6. And we're looking for the probability of being between 60 and 65. Was that it? 60 inches and 65. Well, both of those are to the right of the mean, right? 60 and 65. Okay, that's 60 and that's 65. So we're looking for this area in here. Okay, notice the table only works to the left, right? So first thing I'm going to do is I'm going to figure out what the area is from here down. And that's going to give me everything from there down. And then I'm going to figure out what the area is in here and subtract it from that. So all that's going to get left is this area in here. Okay, so let's take a look at that. Let's see. So let me see here. So Z for 65, I'm going to start with 65. 65 minus 55 over 6 is going to be plus 10 over 6 is going to be equal to 1 point plus 1.667, right? Okay, and so that's going to be the Z-score here, plus 1.667. So what is that area from this point all the way down? Okay, so let's say plus 1.67, 1.67. It's going to be 0, 1, 2, 3, 4, 5, 6, 7. It's 95.25. This is a problem that you brought up, I guess, right? It's 95.25. This area from here down is 95.25, 0.9525. If I wanted to know what percentage of this population was taller than 65 inches, it would just be 1 minus that, right? This area in here would be just 1 minus that.
Okay, so I understand how you got that.
Yep.
But why would you?
I just mentioned that's not part of this problem, really.
Oh,
Okay? Since we just know it's going to be 4.75%, it's going to be that area up there because that's what's left, right? But that's not really what we're interested in. We're interested in this area in here, right? So we know that this is 60. We want to know what's between 60 and 65. So I'm going to find this area here. Okay, so what is that area going to be? Well, the Z-score is going to be 60 minus 55 over 6. That's going to be equal to 5 over 6. What's 5 over 6? 0.833, right? Okay, so what is that area? That area is going to be plus 0.0833. 0.083 is as good as we can get, which is going to be 0, 1, 2, 3. It's going to be 79.67. That area from here down is going to be 0.7967. Okay, 7967. Okay, so this area from here down is 95%. This area from here down is about 80%. So if I subtract this area from that 95%, I'm left with the area that I'm interested in. So the answer is going to be 0.9525 minus 0.7967. Okay? You guys okay with that?
So if you round up the 1.667 to 1.67, this is going to give us the same answer.
It's pretty close, right? It's going to give us, if this were 95% and this were 80%, right? It'd give us 15%, right? And if I actually did this, geez, see how my subtraction skills are nowadays. 6, 7, carry 1. That's going to be, it's going to come close because one's more, right? Let's see, it's going to be 8. That's going to be 1, carry 1 from there. 18 is going to be 2. Actually, no, I don't have to carry that 1. That's a 2. I do have to carry. That's 1 and 1. It's 11. Minus 6 is 5. This is 4. Carry 1 from there. 1, 14. 9 is 5. Yeah, it's 15.58, right? Right. So yeah, it's about 15%. It's almost 16%. Right? So I don't know, depending on how precise we ask you to be, it's always better not to round until you're done. When you're at the very last point, don't round in the, later on, as we move on to other statistical calculations, we're going to be in situations where part of the calculation may ask you to square something. or multiply it by something else. So if you round in the beginning and then you wind up squaring that number, you exaggerate the error. So it's better to keep everything the way it is until you're ready to square. That's why I like using Excel, because with Excel, I don't have to worry about rounding. I just do the calculation. It does it for me. It's in the cell. It's if I want to double it or I have to square it, it's just like an operation that I say to multiply it by itself or something like that, and then it doesn't matter that it's 97 digits, because it'll just take care of itself. Okay, yes. I'm sorry. Yes. Yeah. Could I have done it how? Yes. Oh, you mean like, for instance, in other words, if I had done, this is 65, right? If I had calculated what this area was and then subtracted it from 1, this would have been 0.0475, right? And this area would have been 792, and I could take the two of them and subtract it from 1. I could have done that. But what we did was we took this area, right, and we subtracted this part of it out, leaving this part. Is that what you were after? Or did you have a different way in mind? Yeah. So how did you mean? I'm not sure I understand. And in other words, instead of going this way, go that way? Oh, well, I would have to subtract. Remember, the table only gives us the area to the left, right? So that would be, but that's okay, 79.67, right? 0.7967 is the area to the right. The area to the left would be 1 minus that. And then you could say, well, this area over here, yeah, I think it's easier to do it the way we did it, right? Then it's only, because otherwise you wind up doing an extra operation, right? This way we only have to do one subtraction to get it done. Okay, let's see what else we got here. Okay, this is this is a little bit different, right? This is a real curve here. The tallest 10% of the class is considered very tall. What's the height cutoff for the tallest 10% of this class? Okay, well, this is a little tricky, right? Let me sketch this out again. Okay, here's the distribution, right? The mean is 55. The standard deviation is 6. Okay, so we want to know, this area represents the tallest 10%. The area here is 10%, or 0.1000. That's the area there, right? That's the 10% of the students that are the tallest in this population. We want to know, what height is that, right?
I'm laughing because I just put anything else at 74 inches.
That's a good guess. That might be a good guess. We're about to find out, right? So we want to know what that height is, right? What's that height going to be? Well, what I need to know is, what is the z-score for that height, right? What z-score gives us an area of 10%? Well, just like we use the table here to figure out what the area is from the z-score, we can use the table to figure out what the z-score is from the area. So what we're going to do is we're going to look for an area that represents 10% to the right. But it only works to the left. So we're not looking for 10% now, we're looking for 90%, right? So we know it's not going to be on the negative part, right? You can see these are all, the biggest one here is 50%, right? So it's going to be here. And let's see where we can find 90% here. 0.90, here we go, 89.25, 89.80, 89.97. This looks like the closest right here. Okay, and what is that number? That number is 1.27, right? 1.27 represents the closest to 97%, not up to 90%. So this z-score is 1.27 is the z-score for that value, which represents 90% this way and 10% this way. Okay, now I know the z-score. How am I going to find out what the height is, though? Remember that formula we used before? Z is equal to x minus mu over sigma. I know z, I know mu, I know sigma. The only thing I don't know is x. So I'm going to use it to solve for that. 1.27 is equal to x minus 50 over 6, right? So 6, multiply both sides by 6. 6 times 1.27, right? And the minus 50 goes to the other side, becomes a plus 50. So x is equal to 6 times 1.27, which is, do that here, 6 times 1.27 is equal to 7.62. 7.62 plus 50 is equal to x. So x is equal to 57.62. So any kid that's taller than 57.6 inches is in the top 10% of the population, in this particular population. Okay. Again, these are all just ways of using this one tool, this one table that gives us information about how normal distributions behave, and taking advantage of every little kind of trick we can use to figure out what's below this number, what's above this number, and so on and so forth. So, for instance, if you were operating a ride at the carnival and you wanted to set a minimum height for kids that are in this population, you might say to yourself, "Well, I'm going to make I want to make money, but I want it to be safe, so I'm going to eliminate the lowest 15% of the population, the smallest 15% of kids in this age range. I'm not going to let them take the ride." So how would you figure out what that lowest 15% is? Just the same way we did it now, except now I'm looking at the bottom half, right? Here we go. 55, sigma is equal to 6. So I want to know what's the height, what's the z-score for an area at the lower end that represents 15%, 0.1500. Well, that's going to be a negative number, right? That's going to be 0.0, let's see, 15%. Remember, the areas are in here. 0.15. 0.15. The closest, I think, is that number right here, 1492, Columbus Day, right? Which is that Columbus Day. Negative 1.04. Okay, so I'm going to go back here. So the z-score is 1.04, negative 1.04. That z-score gives us an area that's 15%. But what's that height represent? Again, I just use the z is equal to x minus mu over sigma. Okay, negative 1.04 is equal to 50 minus, I'm sorry, it's going to equal to x minus 50 over 6. Negative 1.04 times 6 plus 50 is equal to x. Now notice this. This becomes then 50 because it's negative. The z-score was negative, right? Now it's going to be negative 6.24 is equal to x. So in other words, that height is going to be 44.76 inches. Anything below that is going to be too short to go on the ride. All right, so like I said, it's just a matter of reading the problem and translating it into how you can use this table or Excel. Excel does the same thing, except you just put it in and it gives you the area, pops out the area. All right, let's see. Okay, here's another, this is another binomial distribution problem, right? Okay, let's take a look at this one. How are we doing on time? We're good. According to Behavioral List, 58% of Americans adhere to a sedentary lifestyle. What will the probability of finding 80 or more individuals out of a population of 100 be less than the probability of 8 out of 10? More than it? The same? Right? Well, you want to know something. The way you could reason this out is if you go to the casino and you play at the casino, right? Let's say that the chances of your winning are just a little less than 50-50, right? 45%, 95, 45%, let's say. Chances are you're going to lose. However, there's a chance you'll win also if you just play once, right? But if you play over and over and over and over again, what happens is that the probability tends to be in favor of the house, because it becomes more and more likely that you will get the outcome that you would expect the house to win on, right? Because just because the sample size is bigger, you're going to get closer to the probability that you would expect. If you don't feel like reasoning it out, what could we do instead? We could actually use a binomial distribution to calculate this. Let's give that a try. Okay, so I'm going to do it two ways. Equals binom dist, parentheses, number of successes, 80 out of 100, comma, 100, comma, what's the probability? 0.58? I think it was 0.58, comma, what's the probability that we would get at least 80 out of 100? Is that what the question was? Probability of finding 80 or more individuals. So it's going to be 1 minus, actually. Okay, 80 or more is going to be 79 or fewer subtracted from 1. Okay, I'm going to put in true over there, hit enter, and that's the probability of that or more. So it's going to be equal to 1 minus this. So the probability of 80 or more is going to be a really small number. How about 8 out of 10? Equal same probability, binom dist. The probability of getting 8 or more is going to be equal to the probability of getting 7 or fewer out of 10. Out of what was it? 10? Is that I got that right? 10. 10, comma, 0.58, same probability, comma, true, and then we're going to subtract it from 1. Comes out to that. Now notice what happened here. The probability of getting 8 out of 10 or more who are sedentary is 13%. The probability of getting 80 out of 100 or more is almost 0, right? Because the odds tend to even out. 58%, you would expect if the probability is 56%, you get 56 out of 100 would be the most likely outcome, right? In the case of sampling 10 people, we would expect to get 5 or 6 because that's close to 56%. So the probability of getting 8 out of 10, that's not so unusual, probably, right? If you're expecting 5 or 6, getting 8 is not unusual. But if you're expecting 56 out of 100, getting 80 would be unusual, right? So that's the way it works out. So you got two ways you can think it out, you can reason it out, or you can just use the binomial distribution to calculate the probability of getting 8 or more, or 80 or more out of 100. Right? And when you do that, you see that the probability of getting 8 or more out of 10 is a lot greater than the probability of getting 80 or more out of 100. That means this is 2.77 times 10 to the minus 6. In other words, 6 zeros in front of that. 0.0000277. Okay, so that would have been the right answer to that. Now, okay, stenosis. Okay, let's see if I can't find that file. Stenosis Bio 610. Here we go. Okay, now this one, the easiest way to solve this one is to use SPSS rather than Excel. A lot of people, if you used Excel and you revert, because when you use Excel, you only see 1 and 0 for male and female, right? If you reverse the two of those, then I'll make sure you get credit for it, because you can't tell if you use Excel. But if you use SPSS, this is really a simple problem. It asks you to do two things. It asks you to find the mean age for everybody, and then compare the mean ages and standard deviations and stuff for males versus females. That's my recollection of it anyway. I could be wrong, right? I'm going to open. I'm going to say open data. Desktop, and there it is. Okay. Good night. To be or not, there's a movie called To Be or Not to Be. There's two versions of it. There's a very old one, and it had a guy named Jack Benny. Have you ever heard of Jack Benny? He was a big comedian, like in 40s and 50s and stuff like that. He has the original version of this movie. And there's a more recent one that has Kevin Kline in it, right? And it's a Shakespearean actor. It takes place during World War II. The actor's wife is secretly part of the underground in France during the war, in occupied France. and they don't want her husband to know about it, right? Because he's kind of not because he wouldn't be in favor of it, but because he's kind of a ditzy and he would like give it away, right? So they don't want him to know about it, right? So the way they would meet is in Hamlet. There's a famous soliloquy, "To be or not to be." It goes on for about 10 minutes, right? And all the actors look forward to doing that, I would imagine, right? So in the play, the way that they meet up, the actor, the woman's contact is in the audience, and whenever he starts to be saying "to be or not to be," he gets up and sneaks off and meets the wife, and they exchange information and stuff like that, right? The only problem is that whenever this happens, he starts to be or not to be. He sees this guy get up and walk off, and this is the middle of the most important soliloquy in this play, and it's driving him crazy. Every time he does this, somebody stands up and leaves the room, right? So I was just going to say as she was leaving, "To be or not to be." But at any rate, that's okay. I encourage you, if you want to go, you can go. Don't worry about it. But if you ever get a chance, catch that movie, "To Be or Not to Be," and if you're really good, catch the original version from the 40s and stuff like that with Jack Benny. Okay, so at any rate, so here's our file, right? Our data is whether a person smokes or not, whether they have lung cancer, whatever the disease is, yes or no, what their gender is, male or female, and what their age is. And I think one of the things that we asked for was just starters. Give us a breakdown of the variable gender. Okay, gender is a nominal variable. So you're not going to find, the mean gender. It doesn't mean anything. The average gender doesn't mean anything. But what does mean something is how many males, how many females there are. What's the percentage of males and females? So I can go up here and say analyze, descriptive statistics, frequencies, because frequencies are counts. Counting, that's what we do with nominal variables. We count them. So I'm going to take gender, move it into the variables. I'm going to also maybe tell it to make a pie chart for me. Okay, or a bar chart or whatever, and I'm going to say okay. And SPSS gives us the relative number of males and females, right? 109 females, 106 males, 50.7% of the population is female, and there's a pie chart or a bar chart that illustrates that. So that's one thing. The next thing it asks you to do is to take the nominal variable age, right? That's, numerical variable age, and to report back what the average age is, what the standard deviation of ages is. And I think also maybe it might have asked you to make a box plot, right? So how do we do that? Well, now we go into analyze, descriptive statistics, but since it's instead of going into frequencies, we go into descriptives or explore. If I go into descriptives, I can take the age, move it into my variables box, and say, okay, and click in options, tell it I want the standard deviation and the mean and whatever else I might want. Click OK, and it'll calculate the mean and the standard deviation for age. But it's going to calculate it for everybody in the population, male and female together. If I want to separate those two out, I go into Analyze, Descriptive Statistics, Explore, and now I'm going to I'm going to move the age into the box that I want to analyze. But now I'm going to go in here and I'm going to tell it to break it down by gender, factor it by gender, male and female. Give me two different results, one for male and one for female. Okay, and I'm going to tell it, gee, I want all the statistics. It's already set up for that. But I also want maybe a histogram, maybe some other stuff. It automatically is going to give me a box plot. And then I'm going to say, okay. Okay, and sure enough, here it goes. It gives me the mean age for females and standard deviation and a lot more information. It gives me the mean age for males and so on. So I can compare the mean age for females, 38, to the mean age for males, which is 45, and so on, and standard deviation and so on and so forth. I can see histograms for those two groups, splits it up into two groups. I can even see box plots for those two groups, right? So that exercise was just to go back to the origins of what we were doing when we first started, to make sure we had the basics of how to use SPSS. So that's what we were looking for there. Some people used Excel for that instead of SPSS for whatever reason. Maybe they weren't comfortable with SPSS. But look how easy it is to do an SPSS. If you do it in Excel, you got to get that big line, a big column of numbers, and you got to break it up by male and female. It's a real headache, right? This is really easy to do in SPSS. Right, and the other thing, if you did it in Excel, If you look at the Excel file, it has 1 and 2 or something like that for male and female. It doesn't tell you which one is which. But in the SPSS file, it tells you right here that 0 is female, 1 is male. Right? It gives you that information. Okay. So I think that's it. That was the last question on there, right? Yeah.
The one I had trouble with was, I think it's 16 and 17.
I heard that number a lot, 16 and 17. So you're not the only one. That number rings a bell. Oh yeah, that's the one with the probability. Randomly, yeah, we did that. That's the 10-year-olds. That's the heights. That's the heights of the 10-year-olds.
That's one that I had trouble with.
Yeah.
But now I'm kind of.
Yeah, see how but this is simple, right? It's not that hard. Yeah.
So in my mind, I didn't realize that the Z table only calculated to the left.
That's right.
I
Yeah.
thought to the left was negative and then to the right was positive.
You want to know something? There are Z tables that will do that for you. We'll give you the area from the mean to the left and the mean to the, from that number to the mean. So what you got to do
Is that why that take 1 minus whatever is important? That gives you the probability, right?
to the other side, to the other side.
So
Okay,
now
so now you see the Z table, if I can get back to it. This Z table, the reason why they put this picture up there is to let you know how it works. So it's always the area, whatever the Z-score is, whatever number you look for, the area is this area that's in the blue,
Okay.
right?
Whether
And
it's
and
negative or
for when it's on the right side of the mean, you look up the Z-score like this number, it's always
Okay,
giving
so
you the
from the
area,
right side
the
to
blue
the
side,
left.
right?
Gotcha. Okay. So that makes so much sense
Yeah.
now.
Okay, and if you use a different Z table,
Now that the test is over,
if you use different, if we use it, we'll figure out some way. If you had a problem with the test, we'll figure out some way for you to like make up for some of that anyway. So if you use this different Z table, let me see if I can't find it. Okay, we'll see what we can do. I know that especially a lot of you guys, this is the first time you've taken this course and taken any math in a long time. See this Z table?
Yeah.
This Z table gives the area from the mean, from that whatever value it is to the mean. It gives you the area that's in the blue, right? So it'll give you that. Right. So you got to be careful. But the majority of them work the way that we use it. See, you'll notice that there's a lot of Z. The majority of them work the way that our table works. But you got to be careful. That's why they give you that little picture up there, so you know how that particular Z table works.